Dear students, in physics we are going to see another very simple experiment. This is from the section mechanics. What we are going to see here is, there is a spring, and if you attach a weight to it, at its bottom part of it, if you attach a weight, the spring will get extended and there will be an equilibrium point, right? There will be an extension and then the spring will come to a equilibrium. When the spring and the mass connected to that are in equilibrium, if you give a displacement to that mass, a small displacement vertically, then what will happen to the mass? You just pull it down and release your hand. What will happen? It will start oscillating up and down. Right? The mass will start oscillating vertically up and down. That will be something similar to a simple harmonic motion. It is a simple harmonic motion. We use or we see simple harmonic motion in the pendulum. A similar format you will see here also vertically. So when there is an oscillation, the oscillation time t and the mass connected to that spring are connected. There is a relationship between the oscillation time and the mass connected to the spring. And what the theory says, look at this. Say this is the spring and you have connected mass m here. Now you give a displacement and it starts oscillating up and down. The time of oscillation t equals 2 pi square root of m over k is the equation. That means t is proportionate to square root m. In other words, if I square this, t squared 4 pi squared, k will come here into m. What is k? K is what we call the spring constant. Spring constant means, depending on the spring's nature, how much force you have to give to get an extension. Say like to get 5 centimeter extension, different springs will require different magnitude of force. Some small springs with 1 Newton force itself, you might be able to get some extension. But think about the springs that we use for shock absorbers, which are very, very rigid. That might need like 100, 200 Newtons or even more than that to get a small extension. So this nature of springs is reflected by something known as spring constant K. For a given spring, that will remain constant. But spring to spring, it will be different. For this spring, it's constant. So if this is the equation, then I can say y equals mx. Why? 4 pi squared over k is constant. So t squared equals 4 pi squared over k into m. That's like y equals mx formula. Which means, how we are going to do this experiment is, we will attach different weights here so that m can be changed. When m is changed, accordingly t will change, oscillation time. So we will measure the oscillation time and then we will draw a graph t squared versus m. First thing we need to see whether it is a straight line, because what we are going to see is verification of the relationship between the mass of a body suspended from a helix spring and its period of oscillation. So we need to check whether this relationship exists. How do we check that? If the graph against t squared and m, if it comes as a straight line through origin, then t squared proportionate to m is verified. Then from the graph, we take the gradient. From the gradient we can find k, because 4 pi squared over k is going to be the gradient, which means k will be equal to 4 pi squared over gradient. That will be the spring constant. Understand? Couple of additional arrangements we will have here. The spring will have an indicator here. It usually has like this. So what we will do, we will fix a stand next to it and we will have another pin here. We call it locating pin. How we fix the locating pin is, Once you have fixed the spring and once you have connected the mass to that, before you let it oscillate, at the equilibrium position where this indicator shows, to be collinear with that indicator, you have to fix this locating pin. What's the purpose of this locating pin? That will help us to count the number of oscillations. That means, look at this, after it starts oscillation, when it goes down and it goes up and again comes down. This is what you call one full oscillation. One full oscillation. So how we can do this? After it starts oscillates, first time when it passes this indicator, locating pin downwards, start the stopwatch. Second time, next time when it passes the locating pin downwards, it's one oscillation. Again when it passes the pin downwards, make sure downwards, because when it goes upwards, it's not one oscillation, it's half of the oscillation. It has to go down, go up all the way and come back. That's what is one full oscillation. So locating pin, when it goes downwards, each time when it goes downwards passing this locating pin, then you can count it as one oscillation. The time we are going to measure for a number of oscillations, not for one oscillation. We will measure the time for, let's say, 20, 30 oscillations, because then we can reduce the fractional error in measuring time. Because stopwatch will have some error, because there will be a least count for that. Let's say the error, maximum possible error from the stopwatch is 0.1 second. 0.1, right. If you are measuring the time for one oscillation, suppose if one oscillation takes 1 second or 5 seconds, let's say, 5 over 0.1 is going to be the fractional error. Whereas, if you measure it for 20 oscillations, 20 into 5 will be 100. It's going to be 100 over 0.1. 0.1 divided by 100. 0.1 divided by 100. Which reduces the fractional error. So, this is something we usually do in the experiments. If there is a method to find the time, because we do the same thing in the pendulum also. In the simple pendulum also, we don't take the oscillation time for one oscillation. We count it for a certain number of oscillations. So that the time that we measure is big, so that fractional error will be small. That's what we are going to do with this arrangement. Materials and apparatus required. You need a helix spring, a set of 50 gram weights to attach to the bottom of the spring and change the weights. A stopwatch, locating pin and a stand. I have shown you the locating pin. Right. So, this is how the arrangement will look like. T 4 pi squared over k into m. Y m x. Don't forget that. If the suspended mass is m, the spring constant of the spring is k, and the period of oscillation is t, t equals 2 pi square root of m over k, t squared equals 4 pi squared over k into m. If the graph of t squared against m is a straight line through the origin, not just straight line, it has to be straight line through the origin, the relation t squared proportionate to m is verified. T squared proportionate to m is verified. Not only that, then from the gradient of that graph, you can find spring constant as well. Let's look at the method. Suspend helix springs vertically from a fixed stand as shown in the figure, and from the lower end of the spring, hang an initial weight of the set of weights. Attach an indicator horizontally to the end of the spring. I have shown that. Like when we do the experiment, I will show it again. When the spring is at rest and close to its path of oscillation as shown in figure, connect the locating pin to the stand in line with the indicator. They must be collinear. Pull down the suspended weight slightly. You have to give a small displacement. Don't pull it like too much. Because the equation is proven for small oscillation with small amplitude. So give a small displacement and release it to make it oscillate in a vertical plane. Measure the time taken for 50 oscillations. It can be 50, 30, 40, 20, a certain number of oscillations, that's all. Using the stopwatch. Obtain this measurement again. Repeat the experiment by increasing m for about 6 values, m of m, and record the values. Right, one by one we will be changing, we will be adding the masses and we will measure the time. Then what we will do? We will draw the graph t squared versus m. Right. Come now, let's do this experiment and see what readings we get. You can see I have arranged the apparatus that are required for this experiment. This is the spring for which we are going to find the constant, spring constant. On the spring, this is how we will be hanging it. You can see there is an indicator as well. An indicator. Suppose if you are using a spring without indicator, then you will have to fix an indicator like this. At the bottom of the spring, you have to fix an indicator. Right. And we are using a locating pin. Why we are using a locating pin is to count the oscillations. I will show you when I make the arrangement, when I fix the arrangement, I will show you how this locating pin is going to be useful. This is the set of masses, right? This is like each 50 gram masses. So, we will be fixing these masses one by one to increase the mass. Told you we are going to change M and measure T, right? So, to change M, we will be using masses. You can see there are different masses, right? Each of this is 50, this is 50. Likewise, there are a set of masses. We need a stopwatch. We have to measure the period of oscillation, stopwatch, right? And we have a stand. On the stand only we are going to fix the spring. We are going to fix the spring and fix the locating pin, and we are going to do this experiment. That's all the apparatus required for this very simple experiment. Let's fix this for the experiment now. Right. This is where I am going to fix this spring. To keep this indicator horizontally on this direction, I will be using another pin here. Look at this, I will be fixing it like this. Right. Initially, we will start with the smallest mass. So, let me remove all these masses. If I remove all the masses, this hook has a mass of 50 gram, right? Let me fix it here. Right. But 50 gram mass, when you substitute in the equation T equals 2 pi square root of M over G, when M is 50 grams, the time will be very less, very short. So, measuring time can be difficult for us. The percentage error might increase. So, I am not starting with 50. Let me fix another 50 here. Now, it is 100 grams. Now, it is 100 grams. The indicator is so high. Let me bring it down. Right. Let me bring it down. It is too high. So, where we have to fix the locating pin is such that when the spring with the mass, when it is in equilibrium, see where its indicator pin is. This is how the indicator pin is. To be collinear with this indicator pin, you have to fix the locating pin. I repeat, when the spring is in equilibrium, look at the indicator pin. Together with the indicator pin, the locating pin has to be collinear. At equilibrium, it has to be collinear. That's how we are going to fix the locating pin. Let me raise it further. Make sure it is in equilibrium. Not yet.
So when you are checking whether it is in the same line, you have to make sure your eye level is at the same level of the pin and the locating pin, and you have to observe it. Then only you can ensure it is at the same level. Now what we are going to do? We are going to give a small displacement to this mass. It has to be a small displacement because T equals 2 pi square root m over k is applicable for small displacement. Oscillation with small amplitude. What will happen when you increase the amplitude? Then the k of the spring constant will not remain constant. Bigger the, like when you increase the amplitude, when you increase the displacement, k might change. Therefore, to do this experiment accurately, make sure you give a very small displacement. So once you give the displacement, look at this, how it oscillates. Look at this. Look at this. That's how it oscillates. It oscillates quite fast. So when we get the oscillation period for one oscillation means, look at this, this is how my locating pin is. This is how the indicator pin of the spring is. When it goes up, right, it goes up and down. When it goes up, you start counting. That means when it passes the locating pin upwards, let's start counting. So it goes up, comes down, and again it comes up to the same point. That is what you call one oscillation. See, goes up, comes down, and again it passes the locating pin upwards. First time you are counting it when it goes upwards. Again, the next time when it passes the locating pin upwards, that is one full oscillation. So measuring the time for one oscillation will be difficult because the percentage error will increase. There will be percentage error, reading error, and the minimum time that we can measure in the stopwatch. Based on all that, there will be a percentage error. So to minimize the percentage error, what we do, we don't measure the time for one oscillation. So we will be measuring the time oscillation period for a certain number of oscillations like 20, 25, 50 depending on the oscillation time to reduce the percentage error. Typically, we say the percentage error in reading must be less than 1%. For that, sometimes we take 20 oscillation periods time or 50 oscillations periods time. Likewise, we take it, right? So what we have to do, if this is a locating pin, when the indicator pin on the spring, when it passes it upwards, you start counting it. You start the stopwatch. Then count 20 oscillations. Every time it passes the locating pin upwards, it is one oscillation. So here I am going to do for 20 oscillations. Let's find the time for 20 oscillations. Then when I draw the graph, I can divide that by 20 and I can find one oscillation's time, the oscillation period, I can find it, right? So let's get ready. The stopwatch is at 0. Let's start it now. Let me give a small displacement to this. You can see it oscillates. When it passes the pin upwards, I am going to switch it on. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 20 oscillations I have taken the time. 20 oscillations I have taken the time, right? 20 oscillations, the time I have got is 16 seconds. 16 seconds. So that is with 100 grams, the 20 oscillation time I have got is 16 seconds. Let's write it down on our table because at the end we are going to draw a graph. So 100 grams is the mass I used. I got 16 seconds as my time. The first reading we got with 100 grams. 100 grams. And for 20 oscillations, the time we got is 16 seconds. 16 seconds. Right? Now what we will do, we'll increase the mass because we are going to take 5 different masses and the respective time. So now, let me add one more mass here. Now it's at 100. Let me add another 50 grams. So when I add 50 grams, you can see now there is 150 grams fixed here. The indicator pin of the spring has gone down. You know, when you give more and more tension, the spring gets more and more stretched. The extension increases. So the indicator pin has gone further down. What should I do? Locating pin also has to be taken down so that it becomes collinear horizontally with the indicator pin. Yes, let's bring it down. Yes, it is collinear now. The indicator pin on the spring and the locating pin are collinear. It's 150 grams. Again, what are we going to do? Give a small displacement, let it oscillate, 20 oscillations, let's get the time. Reset the stopwatch to 0, right? Let's give a small oscillation. It oscillates. When it passes the indicator pin or the locating pin, I'll start it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. This time I have got, look at the reading, I have got 19 seconds I have got, 19 seconds. 1985 I can actually write it as 20. 1985 is almost 20. This is for 150 grams. 20 seconds was the time. That's for, not for one oscillation, make sure it's for 20 oscillations. Huh? So later when I draw the graph, I have to divide this by 20 and find the time for one oscillation. Right? Okay. Now, let's increase the weight. Let me fix another weight now. This is already 150 grams. Fix another 50 here. Now it is at 200 grams. The indicator pin, as I explained earlier, it has gone further down. Let's bring it down now. It's collinear. Yes, it's the same level. Let's give a small displacement. Keep the stopwatch reset at 0. Again for 20 oscillations, we have to get the time. Give a small displacement. When it passes the locating pin upwards, I can start it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. There you go. I have got 22 seconds, and the other reading is 75. You can see that, which I can write it as 23. 2275 is 23. Yeah, this is for 200 grams. 2275 means that's almost 23 seconds. 23 seconds. Now I have to increase another weight. Maybe the height is not enough, because if I fix another weight, you can see it might reach the table level. Look at this. Yes, so it doesn't have enough gap for oscillation. What we will do, we will raise it up. Bring the locating pin also close to that. Right. Now the indicator pin, locating pin are at the same level. Same process again, give a displacement and measure the time for 20 oscillations. Keep the stopwatch at 0, reset at 0. Small displacement, make sure you don't give a long displacement, right, a small displacement. When it passes the locating pin upwards, I am going to start it on. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 20 oscillations, we have got 25 seconds, 25 seconds. 25 seconds we have got. Yes. So that's for 250 grams weight. We have 250 gram mass connected there, 250. And we got 25 seconds. So you can see when the mass increases, time also increases because T squared must be proportionate to M. So if M doubles, T will not double, T squared has to double. So T and M are not proportionate. T squared and M are proportionate. However, when M increases, T also has to increase. We can clearly identify that here. Let me get one more reading because we are expecting a straight line graph. Having 5 readings would be good enough to draw a straight line graph. Let me fix another mass here. That's also another 50 grams. Now we have 250 grams connected there. Lower the locating pin to be collinear with the indicator pin on the spring. Make sure it is in equilibrium. When you check whether it is collinear, it has to be equilibrium. Yes, it is collinear now. Collinear, it's on the same level. Give another displacement, small displacement. Keep the stopwatch reset at 0. A small displacement. Let's start it when it passes the pin upwards. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Right? 20 oscillations. This time we have got 27 seconds. 27 seconds. 20 oscillations. We have got 27 seconds. So this time we have used 300 grams. 300 grams. We got 27 seconds. We have got 5 readings for M versus 20T. Remember, it's 20T. Divide this by 20, you will get 1 oscillations period. Then we can draw the graph T squared versus M. T squared on the y-axis, M on the x-axis. The gradient, it has to be a straight line going through origin. If you get a straight line, then it's verified. What is verified? T is proportionate to root m is verified, or T squared is proportionate to m is verified. And on the straight line, you find the gradient. That gradient's value should be equal to 4 pi squared over k. Gradient is known, 4 pi squared is known, we can find k. The spring constant k also can be calculated. So let's draw the graph and see whether we get the desired outcomes.
You all can see the readings that we have got. I have tabled here. These are the masses that we used, and these are the oscillation times. Yes, that we got for 20 oscillations. Then we have 16, 20, 23, 25, 27 seconds. So T, capital T, that means the oscillation for the time for one oscillation, you divide by 20, you get 1.15, 1.25, 1.35. T squared is required, 0.8 squared is 0.64, 1 squared is 1, 1.15 squared is 1.32, 1.25 squared will be like 25, 12 into 13. 12 into 13 is going to be 156, right? 1.5625, which is what I have rounded to 1.56 there. Similarly, 1.35 squared, 5525, 13 into 14. 13 into 14 is 182. 1.8225 is what I have written as 1.82 there. Similarly, this one also will be 1.3225, which I have rounded to 1.32. So T squared values I have taken and I have recorded here. Now we have to draw the graph. T squared versus M. T squared versus M. M in grams. We need up to 300, isn't it? 0, 1, 2, 3, 4. 50. 1, 2, 3, 4. 100. 1, 2, 3, 4. 150. 1, 2, 3, 4. 200. 1, 2, 3, 4. 250. 1, 2, 3, 4. 300. And the time T squared up to 1.82 we need it. 2, 4, 6, 0.2, 0.4, 0.6, 0.8, 1.0, 1.2, 1.4, 1.6, 1.8, 1.9 would be enough for us. T squared, second squared. 100.64, 100.64, 100 and 0.64, 0.64, 0.64. 151, 151, 151. 200, 1.32, 200, 1.32, 1.32, 200, 1.32, 1.32. 250, 1.56, 250, 1.56, 1.56, 250, 1.56. 300, 1.82, 300, 1.82, 300, 1.82, like that, right? Those are the 5 points that we have got. Now let's draw the line and see whether we get a straight line through origin. If we get a straight line through origin, then it's verified that T squared and M are proportionate. T squared and M are proportionate. That's the graph I get. The first 3 points are on the graph, The last 2 have slightly deviated. That's okay. Usually in the experiments, you can't expect all 5 to fall exactly on the graph. There will be deviations. That's fine. Now we can say Since the graph is a straight line through origin, t squared is proportionate to m. That's verified. Then I need the gradient. To find the gradient, let's take two good points. 2 points. Maybe this one. That's 100, 125, 137.5 and 0.9. We'll take another point. Maybe this one. That is 250, 275 and 1.8. So gradient equals the difference in y coordinates 1.8 minus 0.9 divided by 275 minus 137.5. But this is in grams, isn't it? Let's multiply by 10 to the power minus 3 to make it kilograms. So that's going to be 0.9 into 10 to the power 3. This is just 137.5. And this gradient should be equal to 4 pi squared over k. So k is going to be, let me write it here, k is going to be, let's remove these grids now, right. K is going to be 4 pi squared. Pi squared, can I say 10? Because you know pi squared, pi is 3.14. 3.14 squared is almost 10. Pi squared can be considered to be 10 into 137.5 divided by 0.9 into 10 to the power 3 means 900. Let's multiply. If you multiply that by 2, it's going to be 275. Multiply that by 4, it will be 550 over 90. 0, 0 cancelled. You get 9654 11 kilograms second minus 2. Kilograms second minus 2. That's the units of K. So the spring constant of the helix spring that we have used in this experiment is 6.11 kilogram per second squared. Clear? Right? So that's a very simple experiment. Nothing much complicated in that. So you go through what we have done. At least, twice you have to go through to, remember each step, how we did that and why we did that. Alright. And then practice all this. Now let's see a past paper question that has been tested on the same experiment. Students, let's see a past paper question that has come in this experiment. This is 2008 paper. Figure shows a spring whose upper end is firmly clamped to a rigid stand and a light pointer attached to its lower end. This is the pointer. You are to determine the spring constant K of the spring. A set of standard weights and a meter ruler are provided. Draw the meter ruler on the figure at its correct position in order to measure the extension of the spring. So this is before you have attached the mass. So once you attach the mass, it's going to go down, right? That's what the extension is going to be. So how should be the meter ruler? How should be the meter ruler? Make sure the meter ruler is close to the pointer. Then only you can get the readings. If you keep it far away from the pointer, you can't get the readings precisely. And this must be 0. 1, 2. Likewise, it will go. Understand? So the points you have to note here when you are drawing it, make sure you draw it closer. 0 is right at the pointer and the scale goes downwards, right? Not upwards, because the extension is going to be downwards anyway. Next, the extension values versus load M for such a spring is shown below. E into 10 to the power minus 2, that means it's in centimeters. M into 10 to the power minus 3 kilograms, that means it's in grams. Right. Now what do they ask on this? Determine the spring constant K of the spring in kilogram per meter minus 1. Now you have to be careful about this. what we usually do, look at this. If there is a spring and if M is connected, mg, T will be equal to mg. We usually write as T equals Ke. T equals Ke. Right? But then if this is the equation, K, you wouldn't get this formula. Because this units you wouldn't get it. It's going to be Newton meter minus 1. K will be Newton meter minus 1. Here they say kilogram meter minus 1. So to get it in kilogram meter minus 1, you should not put this in newtons, you have to put this in kilograms. That means the mass that you attach here. So the formula is going to be M equals Ke. Then only K is going to be kilogram meter minus 1. Understand? The graph we have is E versus M. E versus M. So look at this. E is going to be 1 over K into M. Y, M, X. So the gradient is going to be 1 over K. K is going to be 1 over gradient. Let's find the gradient. To find the gradient, you need 2 points from the graph. So look at this. When we take the 2 points, make sure you take 2 points that I always say this. The graph should go through a point where the vertical line and the horizontal line intersect. Then only you can get the coordinate precisely. If you take something, say for example, if this is how the grids are, imagine if the graph is going to be like this. If you take this point, this will be a problem because you don't know the y scale of that. But this point is okay. You know x scale is this, y scale is this. Understand? Right. So now I am using the graph that has been provided here, but make sure like when you do it in the exam paper, sometimes this graph and the original paper's graph could have been slightly different. However, based on the graph given to me here, let me take, see this point is good. Can you see this point is good? Which is, here it's going to be 24 and here it is 3. 24 and 3 and up maybe this point, that's at 62 and 8. Right, based on the graph I have here, those 2 points are good because the graph goes through the intersection of vertical and horizontal scales. From this gradient I can take 8 minus 3 over 8 minus 3 into 10 to the power minus 2 over, because scale is in 10 to the power minus 2, 62 minus 24 into 10 to the power minus 3. This is going to be 1 over K. 5, 10 will go up, 50 over 38. So K will be 38 over 50, which is 0.76. 0.76. 38 over 50 is 0.76. That would be the unit kilogram meter minus 1. Clearly indicate on the graph the 2 points which you have used to determine K. I already have marked it on the graph. I already marked it. You can see here the 2 points. The spring with load M attached is set in vertical oscillations by giving a small displacement. The period T of oscillation is given by T equals 2 pi square root of M plus M by 3 over kg. Now what we usually study is this. T equals 2 pi square root of M over K. Now why this G has come? Because the K that we found here is not in Newton meter minus 1. It's in mass per meter, kilogram meter minus 1. Right? So that's why this G has come additionally. So it's a different K that we are using here. And what's this additional M by 3 here? Where M is the mass of the spring. Spring's mass also will have an impact on, the extension of the spring, which they have factored here, which we usually do not factor it. Right? So that they have included here. Rearrange the above expression in the most suitable manner to draw a graph in order to determine the acceleration due to gravity G and mass m of the spring. Let's square it first. T squared will be 4 pi squared over kg m plus m by 3. Now this m is constant. So T squared will be 4 pi squared over kg into m, 4 pi squared simple m over 3 kg. Y mx c. Check whether everything in C is constant. 4 pi squared is constant. M is the mass of the spring, which is constant. K is the spring constant, which is a constant already. G is the gravitational acceleration, that is also constant. M is constant. This M is what we are going to change, the mass that we attach. What additional instrument do you need to take measurement in this experiment? Like the measurements, we take only the stopwatch, right? The time. They have not mentioned anything about stopwatch. You need stopwatch to measure the time. Stopwatch. What quantities would you extract from the graph to determine G and M? G and M. To find G, the gradient is enough because we already found K. To find G, gradient is enough. To find M, you need both of them, because like if you don't know G, then you can't find M. So first you have to find G from this, and then you go to the intercept and find M. So to find M, you need gradient and intercept. But to find G, only gradient is enough. Only gradient is enough. To determine G, gradient. To determine M, gradient and intercept. Gradient and intercept. If the percentage error of M values is 1%, how many oscillations would you need to take in order to match the percentage error of T also 1%, of T also 1%. Fractional error of T is 2 delta T over T, and error in time measurement is 0.1 seconds. Take T to be 2 seconds. That means one oscillation's time is 2 seconds. They are asking how many oscillations you have to count together to reduce the fractional error to 1%. So it's going to be 2 delta T over, if I am counting for n number of oscillations, nt. This is going to be the fractional error. And this has to be 1%. 1%. So since it is percentage, let's multiply this by 100. 1%. 2 delta T is the error, which they say 0.1 seconds. Did they say that here? Error in time measurement is 0.1. N into T is 2 seconds into 100. 1. 2 and 2 cancelled, N goes up there, N is 100 into 0.1, 10. So if you can get the measurement for 10 oscillations, then that will be giving you a fractional error of 1%. If you will increase it, let's say you get it for 20 oscillations, then the fractional error is going to be even less than this. So that's the reason why we count it for certain number of oscillations. Imagine if it is just one oscillation's time you are measuring, then it's going to be 0.1 over just 2 only. Then 2 and 2 will be cancelled into 100. 10% error you will get. 10% error. Next. A student used a brand new spring whose turns are pressed against each other to draw the graph mentioned in A above. On the figure given below, sketch the shape of the graph that you would expect in this situation. So what's the difference in this spring? The turns are pressed against each other. That means it's to get an extension, right? They are already pressed, right? So if you give small force to it, you may not be able to have an extension. If you give a small force, you may not be able to have an extension. What will happen? M, until it reaches a certain value, the extension wouldn't come because they are pressed against each other. To break that pressing, you need to give more weight. So, the graph will take a shape like this. Look at this. That's how the graph is going to be. After this, it will be straight line. That's how you can expect the graph. For a certain low values of m, you won't see an extension because they are pressed against each other. Right. Since it's a new one, brand new spring whose turns are pressed against each other, we will have this issue. Initially, for small values of m, that wouldn't break that and it wouldn't come out. But after that, after m reaches a certain value, then you can expect the usual behavior of straight line. Clear? Right. So, the last part was a little tricky. Apart from that, all other questions were very simple and straightforward. If you have done the experiment, if you have done the calculations, answering this would have been so simple. Right? Practice all this. What you get in the exam is going to be simple like this. Next, we will meet up with another experiment.